Yeah.
It's Friday.
Right, I know. Okay,
Thank you
yeah.
so much.
Yeah, I remember. I hadn't forgotten. It's on my to-do list. Let's see. Uh, well, the big thing that we're looking for this week is the test, right? So that is Wednesday. So I have posted the answers to the sample test. Taylor was telling me that there were a few mistakes there, so I will show you those corrections in just a second on the answers to the sample test. There's just minor things, and so that's posted, right? Okay, so you're ready now to use to finish using the sample test, right? For preparing for that test on Wednesday. We're going to look at a few problems like that today, a few problems from the sample test today, just as a little bit of additional practice there for the test on Wednesday. Don't forget, you've got a homework due tonight. This homework on log bases other than e, that's due, and then at the time of the test, right, we still have this inverse trig function homework because there's a little bit of this on the exam. So you need to have looked at that homework, especially just differentiating the inverse trig functions, right? The rules for differentiating inverse trig functions. You should look at that. We're going to look at a little bit of that on the sample test here in just a second. When we start talking about that, okay? And then, of course, you've got also this calculus review that's been there for a long time. That's due, and then this optional extra credit homework, right? If you want to do that, quite a few people have done that already, okay? So that's kind of where we are. Taylor said a lot of people came to the review, so that's excellent. So I think that's going to help you a lot on the test, you still have Wednesday before the test to see Taylor. And, of course, you can always go to the Math Center at any time, right, in North 925, or come find me in my office at almost any time. Tomorrow is probably an especially good day to look for me. Well, it has to be tomorrow, Wednesday, right? So yeah, tomorrow's a really good day to come look for me if you need to talk with me before the test, okay? All right, so... that's about where we are. You got plenty of material to prepare yourself for the test. So if you really do take the time, right, to go back through that material, that really improves your chances of having a good test score. I think I opened all the answer keys for the prior homeworks, not the stuff that's due today, but the answer keys for the prior homework. I think I turned on, so you can also refer to the prior homework if there's still some problems in the early homework that you were confused about and never got correct. The answer key's turned on, so you can at least see what the answer is. It's not really a complete solution, but it's just the answer to the question. Okay, all right, so that's where we're at. Do y'all have any questions? Don't forget your survival card. I keep stressing that, but that's really useful, especially with formulas for differentiating inverse trig functions, right? Okay, and other formulas as well, but those really come to mind as things that are hard to memorize that will be useful, at least a little bit on the test, right? But we've had plenty of other formulas too, right? That should go on that can go on there. So take some time to fill out that survival card. That really will, if you take the time to think about it, what you need on there, right? That really will. Not only will the survival card help you on the test, but just the very process of filling out the survival card will help you review for the test. Okay, so, it can be any standard size. So standard size means it's a commercial size, right? Okay. Yeah, it can be 5 by 7, or it can be this size. Yeah, right. But it's got to be a commercial size index card, right? Okay. So one you can purchase. All right. Okay. That's all. That's all sort of the prep stuff here. Any other questions that y'all want to ask? Yes, sir. Are you looking for your questions? All right. While you look at those, let's correct some of the mistakes on the sample test first to get that out of the way. So, but we'll come back to the sample test and do some other problems on the sample test. But let me talk about what the corrections are, because I probably won't get a chance to post this. So here will be your chance to be aware of these corrections. And sometimes this will, this drives you crazy, right? If my answer doesn't agree with your answer and your answer is correct, right? Then, so I think on this first one where you're just expanding this log expression, I left off one of the terms at the end. So I'm not going to go through all the steps here. This is a pretty easy problem to solve without me going through all the steps. But I think I left off this term from the answer key should be there. So the very first one I messed up. That's not a good sign, is it? Okay, let's see. And then down a little bit further here on 4D, where we are differentiating this natural log, okay? So you know how to differentiate natural logs for sure. So the derivative here ultimately turns out to be minus 1 over 3 minus x, and then minus 1 over x, okay? So I think I left off the minus sign. In the first term because I forgot the chain rule, okay? So you don't want to forget the chain rule, or you'll lose points for that, all right? So this minus sign I think is missing from the answer key. Remember, when you think about that derivative, don't launch into computing the derivative too quickly, or you're going to end up having to use the quotient rule at some point, which you'd probably prefer to avoid, right? So before you take the derivative here, don't forget to expand that log expression first, right? That's the log of a quotient. So you can write that as the log of 3 minus x minus the log of 5x, okay? And then that makes it much easier to differentiate. If you just differentiate it immediately, you would, using the differentiation rule for natural log, you would take the reciprocal of this, because that's how derivatives of natural logs work, right? You would take 1 over this fraction. That would, in effect, flip the fraction. So you would have the reciprocal of this fraction, but then you would have to multiply in the derivative of the fraction, and that's going to require you to use the quotient rule. So don't immediately start computing this derivative. Go ahead and expand that logarithm first. That will make your life much easier. So I think that's shown in the solution in the posted answers. But I just missed a minus sign there. Let's see. What else did I forget? Oh, I think on all the way down on 14b, so there's one like we were practicing last time or the time before, where you're told, well, you're not really told anything, but you want to compute here the secant of this angle, and this angle is the arctangent of x. And so you do this by drawing a representative triangle and then deducing what the lengths of the sides are in the representative triangle, and then using that information to compute the secant. We'll look at 14a here in just a moment. It's essentially the same process of solving this problem in 14a as it is in 14b, although this doesn't have a variable in it. This one has a variable in it, but that doesn't really make much difference to the solution. So we'll look at 14a here in a second. However, I computed the secant wrong, so I think the correct answer here is 1 plus 16x squared. Square root of 1 plus 16x squared. I think I have the reciprocal of that, 1 over square root of 1 plus 16x squared, but it's supposed to be just square root of 1 plus 16x squared. That answer. And then, what was the other one? I think there was another one, wasn't there, Taylor? What did I? Oh, there was just 3?
That's right.
Okay, all right, so. All right, so those three corrections. All right. So again, we'll come back to the sample test in just a second and look at some more. I wanted to finish up the notes though from that last set of notes from last time, and I just wanted to make a remark. This is not all that crucial, but we got stumped last time. Remember in class with trying to estimate here the solution to this equation. So we had written down the exact solution, which is 3 plus arcsecant of minus 10 over 2. So we got to that pretty easily, right, by using by applying the arcsecant function to both sides of the original equation and then solving from there. So we ultimately ended up with that exact answer as the solution to this equation. But then we were wondering, well, who knows what arcsecant of minus 10 is, right? So if we want a decimal approximation for this answer, then how do we get a decimal approximation, right? In other words, how do we estimate the arcsecant of minus 10? And we were wondering about that because calculators will compute for you arcsine and arccosine and arctangent, but rather easily, right? A calculator will, but they're not so fast sometimes, depending on the style of your calculator. Not so easy to know how to use the calculator to compute arcsecant of minus 10, right? So we didn't wind up writing down a decimal approximation. Let's see if we can figure this out, though. How can we use the calculator to compute the arcsecant of minus 10? If we don't have a direct way on the calculator of computing the arcsecant function, right? If we only have arcsine, arccosine, and arctangent available to us on the calculator. All right, let me see if we can figure this out. So let's write that down. Arcsecant of minus 10, right? That's what we want to calculate, right? Let's call that temporarily y. All right. I don't know what that value is, but let's call it y, right? Okay. So we're trying to get a decimal approximation for y. Now, y is an angle, right? Y is going to be an angle because it's the output from the arcsecant function, right? Arcsecant function, you put in a number and you get out an angle. Secant function is backwards, right? You put in an angle and you get out a number, right? Okay. So all we really know from this equation is that the secant of y is equal to minus 10. Okay. So secant of y is equal to minus 10. But now once you've got that equation written down, then you can now you can start using your the three standard trigonometric functions, right? Sine, cosine, and tangent. In particular, in this case, we can use cosine, right? Because what is the definition of secant? Yeah, it's 1 over the cosine, right? Okay. So we know here that 1 over the cosine of y is equal to minus 10, right? Because that's the definition of secant in terms of cosine. And now if you multiply both sides by cosine of y and solve for cosine of y, you will get cosine of y is equal to minus 1 over 10, right? See that? So where am I at there? Yeah. If 1 over the cosine of y is equal to minus 10, then just plain old cosine of y is minus 1/10, right? And now, but how do we get back to y now? Remember, because that's what I was trying to determine, the value for y, correct? So how do I use this equation to get back to just plain y equals? What can you apply to both sides? What, Jao? Yeah, the arc cosine, right? Okay, yeah. If cosine of y is equal to minus 1/10, that means that the arc cosine of minus 1/10 is y, right? Okay, apply arc cosine to both sides. So we get y is equal to the arc cosine of minus 1/10. There you have it, okay? That y value is the value that you want, right? So on your calculator, though, you can compute the arc cosine of minus 1/10. Your calculator will do that for you for sure, right? Okay, so that's kind of funny, right? The arcsecant of minus 10 is the same as the arc cosine of minus 1/10. All right, so that's how we can compute arcsecant with the calculator, even if we don't have an arcsecant function available to us on our calculator. Right? Y'all look a little bit confused by this equation, right? What I do, I just applied arc cosine to both sides, right? Of this equation, I applied arc cosine. What happens if arc cosine, when you apply arc cosine to cosine? They cancel, right? So you'll just get y here, and then on the right-hand side, you'll get arc cosine of minus 1/10. All right. So there you can get an estimate for what this number is, right? And then get an estimate for the solution to that equation. Okay, so just wanted to show you that was possible to compute arcsecant with your calculator. Well, sometimes you have to be a little bit indirect about that. Okay. All right, so let's go back now and look at a few problems from the, let's go back and look at a few problems from the sample test. And since we've been talking about, since we were just talking about inverse trig functions there, let's look at some of the inverse trig function problems from the test. Let's look at this problem 14 again that I messed up part B, but let's look at the answer to part A, because you do part B very similar to part A. All right. All right. So this tells us, well, it doesn't tell us much, right? It just says let's evaluate this expression, secant of arcsine of 4/5, but try to avoid using a calculator. Okay, so see if you can calculate this without a calculator. Now you could do it with a calculator, right? By using your calculator to compute arcsine of 4/5, right? Okay, and then apply secant to whatever value you get. Correct. Make sure you're in radian mode. All right. So then apply secant to whatever value you get. So you can get an estimate for this using the calculator. But let's see if we can do it if we're smart enough to do it without the calculator, right? Okay. All right. Let's focus in first on just this part. Okay. Just the arcsine of 4/5. All right. So arcsine of 4/5. I'm going to give that a name. Let's call that y. All right. So I don't have to actually calculate the arcsine of 4/5. Okay, but I'm just going to give it a name, y. All right, give it any name that you prefer. Okay. All right. So what do I? So y is an angle, right? Y is an angle, and so what do I know about y? Not much, but what do I know about that angle y? You know this, right? That's what you know. Okay, so for this angle y, whatever that angle y is, you know that its sine is going to be 4/5, correct? Why do I know that? Because how can you get from this equation to this equation? Just do what? Apply sine, right, to both sides of the equation, correct? So if you apply a sine to arcsine, what happens, of course? They cancel, and then, well, on the right-hand side, you just get sine of y, right? Okay. All right, so you have sine of y. Now, here's what's useful about having this equation written down, though. I'm going to draw a picture of y, all right? I'm going to draw a picture of y. So let's draw that picture, all right? So y is an angle, so I'm just going to embed it in a right triangle here. Going to embed it in a right triangle. Really bad triangle that I drew there, but anyway, there's a right triangle, okay, and here's y, and I know that the sine of y is 4/5, so I can pretend something about the lengths of the sides of this triangle, right? Because in right triangle terms, how is sine calculated? It's what? Opposite over hypotenuse, correct? So in this triangle, I can pretend that the opposite is 4 and the hypotenuse is 5, you see, okay? Because then, indeed, sine of y would be 4/5, correct? Now, you could embed y in a larger or a smaller triangle where this isn't 4 and this isn't 5, but the ratio still comes out to be 4/5, which is 0.8, but this is fine, okay? Just assume that y is in this triangle where this side is 4 and this side is 5. Now, once you know that, see, then you know the length of this side too by the Pythagorean Theorem, right? Because you know when you take this plus this squared, right? Square of this plus square of this, right? That gives you the square of the hypotenuse. So let's write down the Pythagorean Theorem. I'm going to call this side a for adjacent. So I have a squared plus 4 squared is equal to 5 squared. And this works out nicely, right? Because this says a squared is equal to what, 25 minus 16, right? Which is 9. And so a is 3, right? So we get a nice integer value for a, right? It's just 3, okay? Now, look, let's go back. Now we're in shape to answer the original question, because we wanted the secant of the arcsecant. We wanted the secant of the arcsine of 4/5, right? What was I calling this, though? I was calling that y, correct, right? So in effect, what I'm being asked for here is the secant of y, right? But you can now read that off of the triangle, because in a right triangle, how do you compute the secant? Isn't it hypotenuse over what? A, right, okay? It's hypotenuse over adjacent. That's the inverse of the cosine, right? Cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. So you know the answer here is what? 5/3, right? See, we did not have to use our calculator there, all right? We didn't have to use the calculator and still was able to calculate the answer. That's the same, this is the same logic we're going to use on part B, all right, where I made the mistake. This has a variable in it, but the variable ends up making no difference to the problem, okay? You can go through the same steps having that variable x there, all right? Notice we really didn't do any arithmetic right here, except maybe a little bit when we were using the Pythagorean Theorem, right? Okay? So you can carry out this problem just identically to the way you did this, except you have different trig functions involved, but that really makes very little difference if you know the definition of the trig functions. Okay. Let's try see if I can find one here. Let's try I think I have to scroll back. Let's try a differentiation problem with inverse trig functions. So that's way back up here somewhere. Right here. Okay, all right. So this is a very typical problem. You can expect something like this on the exam for sure. There we have a function, pretty straightforward function, right? F of x is arcsine of 2x, and we just all we want to do is calculate the derivative of f, right? Okay, arcsine of 2x. So what do we have to remember, of course, to calculate this derivative? Well, we have to remember the formula, right, for arcsine. I think I have that handy here. Oh, there it is. Okay, so this is in our notes for today, but we can still use it, right? There's the formula for derivative of arcsine. Okay, so remember how that works. Remember, this is arcsine of an expression. Doesn't have to be just plain x. This can be an expression involving x. So if you want to take the derivative of arcsine of an expression involving x, right, you take what? The derivative of the expression divided by the square root of 1 minus the expression squared. Very easy formula if you can remember it, right? Okay, so if you can't remember it, you want to put that on your survival card, right? So derivative of arcsine is a derivative of the expression, right, over square root of 1 minus the expression squared. So in our problem, well, we have arcsine, correct? What is our expression, though, that we're taking the arcsine of? Yeah, 2x right here. So the expression involving x is 2x. That's what the formula calls u, okay? So what's our formula there for the derivative? What goes in the top? The derivative of what? Yeah, the derivative of 2x, right? Which is easy. That's what? 2, yeah. So in the top you get 2. Derivative of 2x is 2. And then the bottom, no derivatives, just 1 minus the expression, which is 2x squared. Okay, that's it. So see if you practiced a little bit with differentiating, these inverse trig functions, right, and you can remember the formulas, then these are really pretty easy to differentiate. So those are just easy points on the test, right? Okay. So that's I think in the homework for that inverse trig homework, That's really what you should focus on, is making sure that you can differentiate these inverse trig functions, right? Okay. Now you are going to have, it's maybe this exact problem or a problem very similar to this in the homework. So I want to go through this one just so you can know how to do it when it's on the homework, right? Okay, this is less likely, however. I wouldn't say this is a high priority to prepare for the exam, but it is on the exam review, so you do want to familiarize yourself with it as best you can, but there are other things that you can study first if you're pressed for time. But there is a problem like this in the homework. In fact, this may be the problem from the homework. Okay, so let's see if we can understand this. This really kind of tests your memory of trig a little bit, but also differentiation. So let's see. An airplane is flying at an altitude of. Let's see if I can remember how to do it. So an airplane is flying at an altitude of 5 miles. Okay. So it's at a constant altitude. So the altitude is always going to be 5 miles. But it's flying toward an observer, right? Okay. So they've got a nice picture there, right? There's the observer that's looking at the airplane. Okay. And of course, there's an angle of elevation, right, from the observer to the airplane. They're calling that angle theta, all right? But remember, the airplane is moving, right? Okay, the airplane is moving toward the observer. So, of course, what's happening to theta? It's increasing, right? Okay, so theta is getting larger and larger. Actually, that's going to continue, right? Even after the airplane flies over the observer. Of course, when the airplane flies over the observer, theta is going to be pi over 2, correct? But even as the airplane then flies past the observer, then our angle theta will be open, right? Okay, it'll go larger than pi over 2, but it'll still be increasing as the plane gets further and further away. Okay. All right. So let's see if we can follow these instructions. All right. So write theta as a function of x. All right, so we want to write down a formula that we can use to compute theta, but that formula is going to be based on x. All right, that formula is going to be based on x. That's what this notation indicates, right? So we're writing theta as a function of, because we're using function notation here, x. So see, what I want to fill into the blank here is some formula involving x. Now, what's x? I forgot to mention what x is. That's another variable that's in the picture, right? X is the distance that the observer is away from the vertical distance, the horizontal distance that the observer is away from the plane, okay? So you can see it diagrammed in this picture, right? Not this distance, okay? Not the actual distance of the observer from the plane, but this horizontal distance from the observer, right, to a point directly below the plane. That's x, okay? All right, so I want to write down a formula there involving x, okay? All right, so, well, there's a very nice right triangle, right, in that, nice right triangle in that picture, correct? All right, so can you write down some expression from that right triangle, right, that involves theta and x? Don't worry about it being a function yet. We'll fix that. But can you write down any equation that involves theta and x from that right triangle that's drawn there? Tangent of theta is equal to 5 over x. Yeah, I think that's right, okay? So tangent of theta is equal to 5 over x. Sure, right, okay? Because how do you compute tangent in a right triangle? It's opposite over adjacent, right? Okay, and we know what this opposite length is. It's 5 because the airplane, right, is flying at at this constant height, right, of 5 miles. And we've got a name for this distance. We don't know what this distance is because it's a variable distance, right? It's changing as the airplane is moving here, right? Okay, but the name we're giving to this distance is x. So there we have tangent of theta equals x. Now that is not theta written as a function of x, though, right? So I need to somehow isolate theta in this equation. So how do I do that? Arc, right, sure, right, okay. So we just apply arc tangent to both sides, right? So, of course, when you apply arc tangent to the left-hand side, you just get theta, and then on the right-hand side, you get arc tangent of 5 over x. There is your function, all right? So just arc tangent of 5 over x, okay? Yay, yeah.
So on the homework, it didn't let me put that in. It had to be cotangent of something like.
Yeah, because but this is correct, all right. But but in the homework, apparently it wants you to write this function a little bit different. And so let me show you what it wants in the homework. And it is a little bit more convenient, I think, actually, to use cotangent instead of tangent. But some people would disagree with me about that because you're just more familiar with tangent than you are cotangent, okay? But I think there's a reason to use cotangent. So the book wants to use a cotangent instead of tangent. So here we know cotangent of theta is going to be what? X over 5, right? Which means theta is going to be the arc cotangent of x over 5, all right? So actually, either one of these technically is correct, right? Okay. But let's focus on this one to solve the rest of the problem, okay? All right. So, but you can use this one as well. Okay. So. Now we're told the speed of the plane is 400 miles per hour. So that is the horizontal speed of the plane is 400 miles per hour, right? So notice that is how x is changing, right? That's how this distance is changing with respect to time, right? Okay. So let's express that speed there as a rate of change. Okay. So we know here that dx dt, the rate of change of x, right, with respect to time is what? But we have to be careful about this. What? Is it 400? If 400 were the, it's something to do with 400 for sure, right? Okay, because that's the speed of the plane. But if we write this down as 400, that indicates that x is increasing, right? Okay, because this is a positive rate of change. But x is not increasing in this picture, right? Because the plane is flying toward the observer. So what should this really be here? Negative, right. So this should be minus 400. So be careful about signs, all right, okay, in rates of change, all right. Now, unfortunately, this is not what we were asked for, okay. We did not want to find dx dt, right, okay. What we want to find is the rate of change of theta with respect to time. So how fast is that angle changing as time is going by, right, per hour, okay? How fast is that angle changing? By the way, is this going to turn out to be positive or negative when we're finished here? We're going to come up with a value here. So is it going to be positive or is it going to be negative? It's going to be positive, right, okay? That has to end up being positive because we know theta is what's happening to theta. It's increasing, right, okay? So as that plane is flying this direction, right, theta is increasing. We already discussed that, correct? Okay, so we know that our final answer is going to be positive, even though this sign is negative. All right, so how do we get to d theta dt, okay? We don't have theta written as a function of t, right? So if we had theta written as a function of t, I would just take the derivative of the function, right? Okay, and then I would have d theta dt. But unfortunately, instead, I have theta written as a function of what? As a function of what? What do we do up here? X, right, okay. We have theta written as a function of x. All right, let me show you now how we're going to get let me show you now how we're going to get d theta dt. Okay, see, this is what we're looking for, right? We're looking for d theta dt, and you practice this process a little bit in Calculus 1, but it probably wasn't your favorite thing to do, so you've probably forgotten it. All right. Again, what derivative am I able to calculate exactly here with respect to theta? I can compute d theta d what? dx, right? I can compute d theta dx, right? That I know how to do because I have theta written as a function of x, right? So if you just compute this derivative with respect to x, you'll get d theta dx, right? But again, not what I want here, all right? But let me show you. Here's the trick we can pull. We're going to multiply by another rate of change, all right? We're going to multiply by another rate of change. Well, there's really only one other rate of change here I have available to me. What is it? Yes, I have dx dt, right? Okay, so let's put that in. So I'm going to multiply here by dx dt, okay? And what happens? That's right. The dx is canceled, correct? And what do you end up with here? Exactly what you're looking for, right? Okay, you end up with d theta dt. All right. So let's just fill in the blanks here, right? Okay. Oh, by the way, remember we want to evaluate this when t is, what are we told here? Yeah, when x is 10. Okay. So I want to evaluate this when x is 10. All right. Well, let's come back to that in just a moment here. All right. So So what is d theta dx? So let's go back up here and let's see if we can calculate d theta dx. Wow. Ooh, that's going to be tough, right? What is d theta dx? So I have to know how to compute the arc cotangent, right, of x over 5, the derivative of that, right? Okay, so I want to compute the derivative of arc cotangent of x over 5. So that's arc cotangent of an expression, right? Here your expression is not just plain x, it's x over 5, okay? Ooh, let's look at our chart of, let's go back and look at our chart of derivatives and see what's in that chart for, there's the chart for arc cotangent. Oh, there it is, right? Okay. Oh, so that's not too bad. We have minus there the derivative of the expression, right? Okay. And then plus, and then over 1 plus, and then the expression squared. So I just negative the derivative of the expression divided by 1 plus the expression squared. No square root. That's nice, right? So let's see if we can remember that back here, right? So let's see. What did I say? It was going to be the derivative of my expression, right? So what's the derivative of x over 5? It's 1/5, right? The derivative of x over 5 is 1/5. But remember, we want to change the sign of that, right? In the arc cotangent derivative formula, it was minus the derivative of this expression. So we get in the numerator here minus 1/5, right? And then what goes in the denominator? So 1 plus what? That's right, 1 plus x over 5 squared, right? 1 plus the expression squared. Ah, cool, right? So here's what we can fill in for d theta dx, right? So let me just rewrite it here. It's minus 1/5 over 1 plus x over 5 squared, right? That's d theta dx. And then you already told me what is, what's dx dt? That's this, right? What's dx dt? Yeah, that's always minus 400. That's constant. Notice no x's or t's in that formula, right? It's just constant. The plane is always flying in this direction, 400 miles per hour. So here, you just have to plug in minus 400. All right, so there's our formula for d theta dt. It looks kind of funny, right? Because it doesn't have what in it? Normally, if you're taking a derivative with respect to a variable, what do you normally get in the formula? Usually this variable, right? So you're thinking d theta dt should involve t, but it ends up not involving t. At least the expression we have does not involve t. But what does it involve here? X. And we want to evaluate this when x is what, though? 10. So, see, they've given us very useful information, right? They didn't give us a value for t. They gave us a value for x, okay? So we want to evaluate this when x is 10. All right, so let's do that just to finish this off. So d theta dt evaluated when x is 10 is going to be minus 1/5 over 1 plus 10 over 5 squared, right? And then times this minus 400, right? So, wow, what does this look like? I have no idea. So minus 1/5 over, how much is this? 5? Is that right? Because this is 2 squared is 4 plus 1 is 5, right? And then we have the minus 400 multiplied in there. So minus 1/5 over 5, I think that's a minus 1/25, and we're multiplying that by minus 400. So notice the result turns out to be positive. Ooh, that's really comforting, right? Because we already knew that theta was increasing, right? So the rate of change had better come out to be positive, which it does. What is this, though? How many times does 25 go into 40? 16? So, so you just get 16 here. By the way, what's the rate there? What are the units of measure? Remember, this is d theta dt, right? So this must be what? No, it's not miles per hour, right? This is d theta dt, right? So it's, what's the unit of measure for the angle there? What units of measure do you use for angles? Could be degrees, but I don't think this is degrees. This is what? Radians. Yeah, this is going to be radians per... No. Hour, right, okay. So it's radians per hour there, okay. That's a pretty big rate of change, but it's per hour. Think about it, it's per hour, okay. And this plane is traveling really fast, okay. So that's why you get such a big rate of change there on theta, okay. All right. So see, you can get through all of those pieces, but that one is a little bit non-standard. That's a little bit non-standard application of our derivatives of our inverse trig functions. All right. Well, all right, let's practice some other things here. Some things I want to just point out to you, okay. One thing we did a lot of, right, in the homework, but also in class, was taking a log expression and expanding it. Probably what we did a little bit less of is this sort of problem where we have an expanded log expression and we want to collapse it, okay? So I'm kind of working backwards here. Here I have 3 log terms and I want to reduce them to a single logarithm. Okay, so we were usually doing the opposite. We had a single logarithm and we expanded it into several terms. Here I want to do the opposite. I've got several terms, and we're going to take a break here in a second. So, but I want to collapse them into just a few terms. Okay. All right. So, well, how do we do this? You're just going to run this movie in reverse. Okay. So you're just, again, going to use these log properties, but in reverse of the way we're usually doing them, right? So 2 times the natural log of x, we can rewrite that as natural log of what? X squared, right, okay? And now, what about this one? Minus 1/2 natural log of z. That's square root, right? So you can rewrite this as a natural log of square root of z. Now, notice here you have some differences, right? And so you've got differences of some log terms here. And how can you combine differences of logs? divide, right? Okay. So if you just want to be patient about this, just do one at a time here. Okay. So let's do these two. So natural log of x squared minus natural log of y would be the same as what? What now? X squared over y, right? And now here you have natural log of minus natural log of square root of z. So how can you combine these two? That also is going to be a quotient. So how can you write that quotient? This is natural log of some sort of quotient. What's that quotient going to be? It's going to be x squared over there, y square root of z. Okay. If you want to think of that in a little bit more complicated way, you can rewrite this as x squared over y, right, divided by square root of z. But x squared over y divided by the square root of z, that simplifies to x squared over y times square root of z. Okay. So that's, again, combined into just a single logarithm. This is also correct, by the way, but this is just a little bit more efficient way of writing it down. This is also a single logarithm, so technically that meets the instructions. This is just a little bit prettier way of writing the answer. So you can go in this direction too, although we didn't practice that as much. Now, I want to remind you, okay, I sort of reminded you of this earlier, but let me remind you again. Here we're computing we're computing derivative of a log. By the way, notice this is not natural log, right? Okay, this is not natural log. This is log base what? 10, right? Okay. So remember, in your final answer, how do you adjust for the fact that this is log base 10? You're computing the derivative. How do you adjust for the fact that this is log base 10 and not natural log? What's going to be in your answer? What now? Yeah, you have to divide by what? Natural log of 10, right? Okay, so in your answer, your final answer, you will divide by natural log of 10. That's to adjust for the fact that this is not that natural log to begin with. This is log base 10 to begin with, okay? But other than that adjustment, computing the derivative of log base 10 is very similar to computing derivative of natural log, correct? Right? Okay. But what step do you want to take first here before you actually try to start computing the derivative? So what do you want to remember to do? What? Expand, right? So do not forget to do that, okay? Here, you want to expand first, okay? So so when you're computing derivatives of logs, make sure you apply your log properties first, right? Okay, so that you don't that simplifies the derivative process, the differentiation process. So I just wonder. So when you see the answer for this on the answer key, you'll see that we expanded that log first, right, before we computed the derivative. So remember to do that. Here's another one now that we didn't focus on this too much in class. There's at least one homework like this, but this is really not a difficult problem. It says you just have to remember the different parts of it. Find the equation of the tangent line to the graph of this function, tangent line to a graph, right, at a given point. So we want to find the equation of that tangent line, right? Okay. So so remember, to find equations of lines in general, whether tangent lines or not, what piece of information do you need to know? So no, not tangent lines necessarily, but just in general, if you want to find the equation for a line, any old line, what piece of it doesn't have to be a tangent line. What piece of information do you need to know? Usually. So what's the first thing you need to know about that line? The slope, right. Yeah, you need to know the slope, right. So to write down the equation for a line, you need to know the slope. That usually involves, in algebra, generally what do you need to write down the slope? 2 points, right? You need 2 points on the line, right? Then you apply the slope formula. But here, to find the slope, right, we won't need 2 points, correct? Because how are we going to find the slope of this is a tangent line. So how are we going to find the slope of this line? By finding the derivative of the function, correct, right? So remember, slopes of tangent lines are the same as derivatives of functions, correct, okay? So here, finding the slope won't be the same as it is in algebra. But after you found the slope, you also need at least one other piece of information. What do you need? To write down the equation for the line after you have the slope. A point. Yeah, you need a point that goes through that the line goes through, right? Okay, you need at least 1 point. Usually now in algebra you'll have 2 points because you've had to calculate the slope, right? Okay, but that may not be the same in calculus. You may not have the 2 points. But here we do have a point that the line goes through, right? Okay, because we want to find the tangent line at this particular point on the graph of the function. That point lies on the graph of this function. So that's the point that our tangent line is going to contain, right? So we've got the point, and now we need to know the slope, but we know the slope by finding the derivative, correct? So really this just boils down to finding the derivative of a function, right? This is a roundabout way of asking you to find the derivative of this function, x. Now, the reason I pointed out this example, or the second reason I pointed out this example, not just for tangent lines, just to remind you of how you find equations for tangent lines, but to find the derivative of this function, you need to remember to use what? What rule from what? Well, yeah, we need to know, so there's actually several rules, right? We need to know how to find derivatives of logs. We need to know how to find derivatives of exponential functions. But even more primitive than that, we need to use what rule? The product rule, right? So do not forget the product rule, okay? This is the product of two expressions. So to differentiate this, you need to use the product rule, okay? So just a reminder, these rules from calculus still apply, right? Okay? Rules for differentiation from calculus still apply. Product rule, quotient rule, power rule, right? Okay, those chain rule, those are really the basic ones, correct? Okay? So you still need to be familiar with those, and you still have to use them from time to time. So let's see, f prime of x is going to be, well, let's see, the product rule says what? I take the derivative of e to the x and then keep the natural log, but what's the derivative of e to the x? E to the x, how easy, right? Plus, and then you keep the e to the x, right? And then you take the derivative of natural log, which is what? 1 over x, right? So you see you get a really easy derivative. And then we want to evaluate that to find the slope of the tangent line, right? We want to evaluate that at x equals 1. This is the x-coordinate of the point that the tangent line goes through, right? So we evaluate this at x equal 1. So we get e to the first power times natural log of 1 plus e to the first power times 1 over 1. But what's natural log of 1? 0. So this goes away. So it looks like I just get e. So a weird slope there. The slope of this tangent line is e. Okay, remember that is a number, right? That's approximately 2.71828, etc. Right? But it is a value, so we can certainly use it for a slope. So there we've got the slope, right? And there we've got our point. So now we just use the point slope form to write down the formula for the line. So I would say what? Y minus the y coordinate of this point is equal to that slope times x minus the x coordinate of the point. Or you can add the y coordinate on the right hand side too, but since it's 0 it doesn't make any difference, right? So you just get y is equal e times x minus 1. There's the equation for that tangent line. So you see that's really an easy problem. Don't get just thrown off there by having to recall what does tangent line mean and how do we find equations for lines. Those are things that you've done many times. Okay, so don't let that basic knowledge throw you off, right, on the test. Ooh, wow, there's a tough problem. Well, we've certainly seen examples like that in the notes, so you can look at the solution to problem number 8. I'm not going to go through that one. explicitly, but you've got the solutions posted. All right. Now, of course, a lot of the questions on the test are going to be antiderivatives, right? Because a lot of the class is antiderivatives, as you are already aware. So this problem number 9 is just a whole series of finding antiderivatives. And so we're not going to go through the problems one by one. Again, the solutions are posted, so you can look at the process for finding these antiderivatives. I just wanted to go through with you, though, sort of what your initial thinking would be for each problem. In other words, what technique suggests itself as the proper integration technique, right? So when you first glance at this is a big part of being successful in calculus. When you first glance at an integral, can you determine fairly quickly how you're going to attack, what method you're going to use to attack that integral, right? Okay. Now, you might be wrong initially, but you need to start somewhere, right? But most of the time, you'll be correct, right? But if you practiced enough. Ooh, man, I'm not sure. Okay, maybe I do. So in 9A, what would you suggest there? Yeah, substitution, right? Okay, I would try substitution immediately. And what would you substitute for? Yeah, the denominator there, I think x squared plus 4, right? Okay, that I think is going to work out nicely. I think that will be just a perfect substitution. Look, here's why we would try substitution. We frequently use substitution, right? So, that's kind of a default choice anyway. So maybe you don't even need an excuse for using substitution. But what I would look at here is, all right, so we have this denominator, right? X squared plus 4. What's its derivative? 2x, which already is in the numerator, right? So you have a derivative divided by an expression, right? And that is suggestive of integrating with natural log, correct? And so we just have to figure out just what the proper integral is going to be, and that's what the substitution helps you with, correct? But that's why you would say, oh, I'm going to try substitution. What about this one? Same thing. Yeah, same thing. I would try substituting for the denominator, okay? I would try substituting for the denominator. Now, this one is not as clean cut as this one, but it's pretty close. What's the derivative of 1 minus 5x? Negative 5. You don't have negative 5 here, right? But negative 5 is just a what? Just a constant, right? Okay? So you're just off by a constant from having a derivative divided by the expression, correct? Okay, you're just off by a constant. If that's the case, then substitution is going to be a good way to go. Okay, so again, you would just try substitution for the denominator. What about here now? So don't get carried away with long division, right? Okay, so here you would try long division because the degree of the top is bigger than the degree of the denominator. So we would start with, I think, trying long division. Okay. What about this one? Substitution, right? That one's going to be substitution. Again, what you're looking at there? Oh, by the way, what are you going to substitute for? Yeah, the minus x to the fourth, right? You're going to substitute for this exponent, correct? And again, the reason why you're thinking, ooh, substitution might work here is, what's the derivative of minus x to the fourth power? It's the minus 4x cubed, which is almost what we have here, right? Okay? See, whenever you have an expression times its derivative, right, then substitution is, usually just really ripe, okay? So yeah, substitution. What about here? Same thing, right? Yeah, this is going to be substitution, right? Now, it's going to work a little bit different from this one because the base is what? 10, right? Okay, it's not e, but that's still an exponential function, right? That's still an exponential function, just with a different base. So you can still integrate this. Remember, you'll have to slightly adjust your answer, right? Okay, by, I think, dividing at the end by what? natural log of 10, right? Natural log of 10. But but again, the reason substitution is going to work nicely here, and you're going to substitute for the exponent is, what's the derivative of 2x? 2. You don't have that multiplied in here, but 2 is again just what? A constant, right? So remember, constants usually don't bother you that much when you're doing integration, okay? Because you can factor them out of the integral, right? Okay. Ooh, what about here? Any ideas there? Substitution, right? You're going to use substitution for x minus 3. Don't do x minus 3 squared, okay? Just x minus 3, right? Because what's the derivative of x minus 3? 1. There it is right there, right? Okay. So I'm thinking, yeah, x minus 3 looks like it will be a good substitution because its derivative is multiplied in here, okay? All right, so substitution there with x minus 3. Same thing, okay? Substitute x minus 3, all right? But this one is going to require more work, all right? So the substitution is not going to go nearly as nicely as it is here. So this one does require some steps, all right? But you would try that with substitution, okay? This one also is substitution. Substitute for the denominator. Again, that's going to require a little bit of extra work. This one, yeah, substitution for what here? Not the whole bottom, I don't think. E to the 2x? Well, you might try actually e to the 2x minus 9, okay? You might throw the minus 9 in there. You may be able to do without that also, okay? But I would try substituting for e to the 2x minus 9, okay? Again, why would, not square root, not the square root, just the quantity under the square root, right? Because what's the derivative of e to the 2x minus 9? It's, yeah, e to the 2x times 2, right? Don't forget you have to multiply in the derivative of the 2x. So it's 2e to the 2x. You don't care about the minus 9 because what's its derivative? 0. So you get 2e to the 2x is the derivative here of this quantity under the square root. But what do you have in the top already? Yeah, e to the power 2x. What are you missing? The 2. But we usually, again, that's a constant. So we're usually not concerned about missing that constant, right? Okay. So see, I'm thinking, I have this expression. I have its derivative. That would be a good, or almost its derivative. That would be a good substitution to try. Okay. Okay. So, well, even after you've done the substitution, of course, there are plenty of steps left, right? Okay. But again, you've got the solution, so you can see the solutions here on your on what's posted. All right. I think. Oh, maybe. Oh, that's it. All right. I did not circle for us to go over. We've done this plenty of times, but I don't want you to forget how to find turning points, right? And how to test turning points. How to find inflection points and how to test inflection points. So there's a problem for both on the sample test. So don't forget those processes. They're kind of complex, right? So if you need to review those, make sure you've reviewed those before the test, okay? Because I'm pretty sure we will have one problem where you're asked to, locate turning points or locate inflection points, all right? And maybe test those turning points and test those inflection points to see if they're really genuine or not, okay? So be sure you've reviewed that process. Again, you can see that illustrated in the solutions here to the test. Did y'all go over one of those?
Yeah, we did that one.
Okay, you did that one? All right, so some people have already seen that if they went to Taylor's review. But you still have a chance, remember, on Wednesday, right, if you've got time, right, to go to Taylor's review before the test and ask questions about this sort of problem or any other sort of problem, right, before the exam. Okay, all right, so let's stop there for a minute. Let's take a few minutes, and then we're going to come back and talk about how we're going to apply the derivatives of inverse trig functions. it's fun to differentiate those, but that's not really what we're after when we learn the derivatives of inverse trig functions. I'll show you. Our goal is really integration, not differentiation so much. So we'll talk about that when we come back in a few minutes here. Okay. Okay, we're going to resume here and switch to some new notes, all right, where we're going to, again, apply our knowledge of differentiation of these arc-trig functions to help us do integration, all right. So there's just a reminder of the derivatives of the arc-trig functions, right? And although we used this one today, we're really, these are really the ones that are most important to us. A derivative of arcsine and arctangent and arcsecant, okay? And that's because from those three derivatives, we can derive some useful antiderivative formulas that apply for a surprising number of expressions. And so here are the three key formulas, antiderivative formulas that we're going to practice in this next homework in these notes. Again, using these formulas is based on recognizing the pattern or the form of the integrand, right? So if you have an integrand of this form, where you have a square root of difference of two squares, but notice it's a constant squared minus an expression squared, all right? Constant squared minus an expression squared, and then you have the derivative of the expression in the numerator, okay? So we've seen that situation so many times, right, throughout the semester, right? You have the derivative of this expression in the numerator. But again, look at the form of the denominator here. It's square root of. You must have a square root there. And then it's constant squared minus expression squared. That's difference of two squares, which is a frequent pattern of expressions that we encounter in algebra. All right. Then we can integrate this type of expression. Okay. And surprisingly enough, the integral here, the antiderivative, involves the arcsine function. All right. So it's arcsine just of the expression divided by the constant that was squared here, not the square of the constant, but the constant itself, right? That was squared, and then of course plus our arbitrary constant. All right. This type of integrand now will occur kind of frequently. So, or things similar to this will occur kind of frequently. That's why this antiderivative formula is useful to us. All right. What's really interesting, and this comes from, this is just a direct consequence of taking the derivative of the arcsine function. That's where this antiderivative formula comes from. Okay. So now again, well, not again, but what's interesting about this antiderivative formula is notice that this expression is completely algebraic, right? This is just an algebraic expression, kind of a common algebraic expression, right? The reciprocal of the square root of difference of two squares. And notice that, but the antiderivative involves an inverse trig function. So here we have a relationship between just pure algebra and trigonometry, okay? Kind of an unexpected one, right? Who would think that the antiderivative of an integrand like this would end up involving an inverse trig function, okay? But it does. All right, now, also a pretty commonly occurring expression here is reciprocal of sum of two squares. See, notice in this denominator you have sum of two squares. Constant squared plus an expression squared. Notice it's not square root, okay? Not a square root there, though, okay? Just a reciprocal of sum of two squares. And that also we can integrate using inverse trig function. It turns out that the antiderivative of that is 1 over the constant. Notice you have this coefficient here of 1 over the constant. That doesn't occur in this antiderivative formula. But here you have 1 over the constant times the arctangent of, again, the expression divided by the constant. All right? So notice the pattern of the integrand. It's the reciprocal 1 over sum of two squares, okay? So when you see 1 over sum of two squares, then you know you're going to have a good chance of integrating that using the arctan function. All right. This one's a little bit more complicated, okay? So maybe it doesn't occur as frequently, all right? So here we have, in our denominator, we have an expression times the square root of, and again, notice it's difference of two squares, but here, the difference between this and this is, notice here the expression comes first, and the constant squared comes second. So this is constant squared minus expression squared. This is expression squared minus constant squared, but also notice the expression is outside of the radical, okay? So if you have an integrand that looks like this, you can integrate that as well, and you use the arcsecant function to do that, okay? Notice this antiderivative formula looks kind of like this one, right? It's 1 over the constant times the arcsecant, not arctangent, but arcsecant of expression divided by the constant, but notice that it's the absolute value of the expression divided by the constant. That doesn't happen here in this one, but here it's absolute value of the expression divided by the constant, and then plus your arbitrary constant, okay? So those are going to turn out to be useful for us integration formulas. All right, so that's it, okay? That's what we're going to practice in these notes, are those three antiderivative formulas. So all we have to do is recognize which one of these formulas, if any of them, is going to apply, right? Okay, to find a particular antiderivative. Let's try a few of these, and these are pretty straightforward examples, I think, to start with. All right, so here these are just indefinite integrals. We're just finding antiderivatives, right? Not definite integrals, so we don't have to evaluate the antiderivative once we find it. We just have to find the expression for the antiderivative, okay? So, so when you look at that, all right, when you kind of look at that, maybe the first thing you should notice there is the square root, right? Okay, so that's kind of a tip-off that you might be using one of your arc-trig functions to write down the antiderivative, okay? But you don't want to jump the gun necessarily here, okay? You may end up just using plain old substitution without using one of the antiderivative, one of the inverse trig functions, okay? But here's kind of the clue that we're going to use an inverse trig function. Look, so, of course, in this denominator, we have square root here, and then under the square root is the x squared. What is the derivative of this thing under the radical? It's minus 2x, right? Because the derivative for it is 0, all right? But you do not have in the numerator minus 2x, right? Okay. Now, the minus 2 is really not the issue, but you do not have in the numerator the x, okay? That's going to cause you a real problem for straightforward substitution. So you might think, oh, I'll just substitute u for 4 minus x squared, all right? And proceed, okay? But you're going to run into problems doing that because the derivative of 4 minus x squared is minus 2x, and you don't have the x here in the numerator, okay? So I don't think just plain straightforward substitution is going to get us very far. We could try it, but I don't think it's going to get us very far, okay? So see, that's a really important thing to notice. So had the original antiderivative, had the original integrand look like this, then you could have used just plain substitution, I think, okay? Again, because the derivative of 4 minus x squared is minus 2x. We don't have the minus 2, but we would have the x. So we wouldn't worry so much about the minus 2 because that's a constant, right? Okay. So I think we would just let u be minus 4x and see what happens. But without the x, that's not going to work very well. All right. But we're not at the end of our rope. Okay, right? Okay. Because now we also notice what? I have in this square root, what? What kind of expression is this? It begins with a D. That's difference of two squares, right? That's difference of two squares. So when you have in your denominator square root of difference of two squares, then you should be thinking, that might integrate using what inverse trig function? Arcsin, right, okay. That might integrate using Arcsin, all right. So let's see if we can integrate using Arcsin, all right. So to integrate that using Arcsin, right, remember you need a constant squared minus an expression squared. Is this a constant squared? Yeah, that's what quantity squared there. 2, right. So you see, you can think of here a as equaling 2, right? Again, I'm doing that to sort of match. I'm doing that, right, to see if I can kind of match this pattern, right, in this formula. So if a is 2, of course, a squared would be 4, right? Now, what about the u here? So what's the... Just x, right? Okay, yeah, u is just going to be plain old x, right? Okay, because the expression here is x squared, right? Okay. All right. Well, let's try making this substitution. It's kind of a silly substitution. It's so easy. What's du dx? What's the derivative of x? 1. So that means that what? Du is equal to dx, right? Okay. And so let's see what we get here. So we have dx. Well, dx is the same as du, right? Over the square root of, and then let's see what, this is 2 squared, right? 4 is 2 squared, correct, right? And minus, and then x is u, so we have u squared. So look, see, we've got this pattern matched exactly, right? Okay, you've exactly got that pattern. The a is 2. You have 2 squared, right? The x is u, right? So, so we automatically know how this is going to integrate, right? Without any extra work, we can just write down immediately here what the antiderivative is going to be, right? So let's see. That is what? Arcsin, right? Of u over what? 2, right? And then plus our arbitrary constant. But, of course, u is really x, so I could write this as arcsin of x over 2 plus a constant. See how easy that was? That wasn't really much of a substitution there because u was really the same as x. So you probably could have figured this out without plugging in u for x. I think you could have figured out the answer was going to be arcsin of x over 2, right? Well, let's look at this one, okay? So again, you might think a natural thing to start with is I don't want to, I hate inverse trig functions, so I don't want to deal with inverse trig functions. So I want to see if I can integrate this just by regular substitution, like we've been doing up until now, right? So can I just substitute u for this denominator? We did. I just saw a lot of examples like that, right, on that sample 1 test, right? Okay. But if we just think of substituting u for the denominator, what's the derivative of the denominator? 18x, right? Okay. And do I have that in the numerator? Unfortunately not, right? Okay. The 18 is not the issue. I don't have the x, right? So if you try substituting for the denominator here, you're going to end up with a mess. Okay, you're not going to be able to cancel your x's, so you won't be able to change variables. So plain substitution is not going to get you anywhere. But let's see, does this look like arctangent would work, right? What's the clue for arctangent? Of what? Addition of 2 squares, right? You want sum of 2 squares in the denominator. Let's see, is 9x squared a perfect square? I think so. What quantity squared gives you 9x squared? 3x, right? Okay, yeah, 9x is 3x squared, right? Okay, so that's a perfect square. Now, 2 is not a perfect square, okay? 1's a perfect square and 4 is a perfect square, but 2 is not a perfect square. But we can fudge to make 2 a perfect square. We can write it as what number squared? No, 2 to the 1 squared would be 4. No, 2 to the 0 squared is 1. 2 to the 0 is 1. Squared is 1, right? Okay. But you're in the spirit of it. What thing squared would give you 2? what quantity squared is, in fact, 2? Square root of 2, sure, yeah, okay. It's square root of 2, right, okay? Just by definition, right, the square root of 2 is 2, correct? Okay, that's what makes the number the square root of 2. When you square it, you get 2. So we do have a constant squared here. It's, it's not a whole number, but it's a constant, right? Okay, so we do have the factoring pattern for arctangent, for using arctangent to integrate, right? So let's see, what would our substitutions be here? The a obviously is square root of 2, right? Because that's the constant we're squaring. More important here is u. What's u? 3x, right? So what's du dx? 3, right? Which means that, what's dx there? Du divided by 3? Yeah, okay. So that's du divided by 3. And so now those are the substitutions that we will make here. So we actually are doing a substitution, right? It's just not a straightforward substitution like before. So let's see, I have minus dx, but dx is du over 3, and then divided by, this is square root of 2 squared plus u squared, right? Because I'm going to substitute u for the 3x, correct? And now you're just in great shape, right? You can factor out the, this is a minus 1/3, so I can bring that out in front first. So I'm going to factor out a minus 1/3, and so that leaves me with du over, and then again, square root of 2 squared plus u squared. But now that is easy to integrate, right? So we have minus 1/3 times, how does that integrate now as arctangent? Do you all recall? So you get 1 over the a. That doesn't show up in the arcsine integration, but it does show up in the arctangent integration at the front. So you have 1 over square root of 2 times the arctangent of, and then your u here divided by square root of 2, and then plus this constant. And now you have to undo your substitution for u, but that's easy. So let's see, it looks like minus 1 over 3 square root of 2 arctangent of 3x over square root of 2 plus constant. So that, all of that is the answer. So see, that's a very impressive answer. Looks like it would be really difficult to arrive at, but it's really not. Okay, it's really easy, pretty easy antiderivative to discover in terms of as far as antiderivatives go. All right, let's try. I'm going to let y'all try one here. Okay, there's the table. All right. Okay. So you want to see if you can integrate this. It's going to you're going to use one of these. You're going to use one of these formulas, right? Okay. All right. To try that one. So see what an appropriate substitution would be so that you can use one of these formulas, right? That means figure out what the u is. Okay. Right. And to a lesser degree, figure out what this constant squared is, right? Okay, and then see if you can make those substitutions, and then write down the antiderivative, okay, with the formula. All right, so y'all try that one. Taylor and I will assist as needed, okay.
To do this thing, right? Like where you solve for number 2.
Do I have to do that?
I think you do. Because here you is 2x and it's, so I did that right?
Yeah, so that's right. So this is x, right? So But let's see. But when you yeah, right. Okay.
I was kind of stuck on it for a second, so I'm just making sure I did it right.
But do we have to?
I think we do.
I think we do, right?
Because
yeah, right.
Not,
yeah, so
yeah,
unfortunately that's not 2x, right? So we do have to be a little bit clever about that. But then we can immediately. Ooh, how does that? Oh, that comes out as a 2, right? In front.
Yeah, we get du over 2, and then these two 2's cancel each other out.
Yeah, these two 2's cancel each other out, right? Yeah. Oh, I
see.
see.
Then it actually works.
Then
it works out.
It does work out,
yeah.
right? Oh, okay.
Oh,
but you have to remember. But you have to
remember to. You have to know to do the.
Yeah, right. But I was thinking, do you really have to do that first? Maybe you do.
Yeah, because if not, you just have an x there.
Yeah, because you do have to get rid of the x, right?
Well, I skipped a step. Yeah, I could have.
Right.
Had an x there.
Okay, so we'll have to prompt people on that. There's one little trick in this one, but it's not really that hard. But Taylor and I will show you this. So, wait, what are you letting you be there? No, you're missing your original substitution, right? Okay. So how do you write 4x squared as a perfect square? Yeah, it's 2x squared, right? So u is going to be 2x. Yeah, u is going to be 2x. Right. Okay. Now, so you have to be careful about how you replace this x, because this is not 2x, right? So you can't directly put in u, right? But solve this for x so you can see what does go there, right? Okay. Are you stuck somewhere?
Yeah, actually, I think you were explaining to her that you can't.
Yeah, that's right. Yeah, this is a little bit tricky because so this is correct, right? You got this right. All this is right, but where did this 2 come from?
Because I just assumed that because the thing is, it has to be the same u, right?
It has to be the same, right? So we have to be a little bit careful about that. So this is really just x, right? But how? Yeah, for x here, what is x going to be here?
U divided by 2.
Yeah, so that's what you put right here is u divided by 2. So you do get the u there. See, this is going to be u, right? So you will get the u there, but it's u over 2. But a nice thing happens because this is du over 2. So these two 2's actually will cancel each other. They end up canceling each other. So you just get du over u.
Okay.
Yeah. Okay. Yeah, you have to be careful about getting rid of that x when you that's in front of the radical when you make your substitution. Okay. Yeah, that's a good way of writing it. Do you see that?
I'm still working on my substitution.
Yeah. All right. So oh no. So yeah. So what? Oh no. This is just. So u is 2x, right? So what's du dx? What's the derivative of 2x?
2.
2, not x. Right. Yeah. But all right. So that means you can solve for dx, so you can get rid of the dx, right? Yeah. So dx is du over 2. All right, so we can get rid of this by substituting u squared. We can get rid of this because that's du over 2. This though is the issue. How do I get rid of this x? Because u is 2x, not x.
Right.
But if u is 2x, then how much is x? Solve this equation for x. Yeah, if 2x is equal to u, how much is x? Just by itself.
Oh, then would it be x is equal to u over 2?
Yeah. So now you can put u over 2 here, right? When you're doing your substitution. And something's going to happen to that 2 that's there.
I don't know if this is allowed. Could I just pull that 2 in front of that x?
Oh, you just pulled this 2 in front of this x? Yeah, that is allowed.
Okay.
So that's an unusual way of thinking of it. That's correct. Yeah, it works.
Right.
So you get, but this is a squared.
Oh, right.
Yeah, and it's u squared. Yeah, minus a squared. Yeah, there you go. Right. Okay.
Also, do we need to include these formulas on our cheat sheet? Is it necessary?
Not these. These are not on the test. Yeah, these integration problems, remember, are not on the test, right? This is new stuff.
I think from the previous problems, we didn't have the x here, so I'm wondering how do we get rid of this x?
Well, let's see. So you have u is 2x, right? So what's du dx? What's du dx? Take the derivative of u with respect to x. What's du dx? What's the derivative? 2, yeah. Now solve that for...
So it's going to be du over 2 equal dx, right?
I think so, yeah. So du over 2 is equal to dx. So that you can... Yeah, so that you can plug in here, right? This is going to be u squared, because this is u, right? 3 squared. But now we have to get rid of the x. So you know that u is 2x, right? But what is just plain x going to be then? So if this were 2x, I would just write u here. But this is u is equal to 2x. So how much is just plain x equal to? Solve this equation for x.
Oh, is this x equal to?
No, if u is 2x, then how much is x equal to?
If u is 2x,
How much is x?
how much is x? Don't know. I really-
Yeah, but you can solve that, right? By
x
doing
equal
what?
negative 2, right?
No. How do you get rid of the 2 here? If you have 2 times x, how do you get rid of the 2? Divide, yeah, right. Okay, but you have to divide both sides. So x is u over 2.
Oh, okay.
Yeah, so here put u over 2 to get rid of that.
Yes, sir.
So see, now you have everything gone, right? You have u over 2, square root of u squared minus 3 squared, and here you have du over 2. Now something's going to happen to those 2's, so look what's going to happen there, okay? Did you get it there? Is that it? Yeah, I think that's it, right? Okay. Nice there. Did y'all get something? I think that's right. Looks right. Okay.
Yeah, we all got that.
You all got that? Okay. All right. Did y'all get something there?
I got this.
I think that's right. Yeah. Okay. Cool. All right. Excellent. Absolute value, though.
Okay.
Just kind of a technicality.
Okay.
Yeah. Nice. All right. All right. That's good. Oh, wow. Y'all ready for the homework?
Yes, sir.
But this is not on the test, so this is on the... I haven't posted this homework assignment yet. The test is only through the stuff that's posted, only through that first homework on inverse trig functions, right? All right, so I think y'all did that very successfully. The answer there comes out to be, I think, 1/3 is it secant? Yeah, arcsecant of absolute value of 2x over 3 plus a constant, right? Okay. Your substitutions are u is going to be 2x, and a here, the constant squared, is 3. The only tricky part is how to get rid of this x, right? When you do your substitutions, you can of course substitute u squared for 4x squared, but what do you plug in for x? Well, if u is equal to 2x, right, that means that x by itself is u over 2. So you can substitute for x, right? It's just u over 2. And then a nice thing happens. The 2's in the problem end up canceling. And so you end up with this integral, I think, just du over u times the square root of u squared minus 3 squared. Once everything cancels. And that then, of course, you integrate that using arcsecant, and then undo the substitution, and you will get 1/3 arcsecant, absolute value of 2x over 3 plus a constant. All right, so I think most people got to that point. Great. All right, so there's our first little taste of integrating using inverse trig functions. All right, so we have more practice to do with that, but we won't come back to that until Monday, because we have the test next time. All right, so I'm going to see y'all on Wednesday, right? Okay, so study well. I know y'all are capable of high test scores. I can tell this. So let's live up to our potential. Let's earn that good grade early. You know that advice, earn your A early? That early in the semester? That's really good advice. Okay.